capturing liquid gold condensate was actually requested by several past audience members who wanted us to go out into the system beyond the boiler room walls and discuss pertinent information which would broaden their overall steam system knowledge while assisting them in improving their operations relating to saving energy, improving the process, and as always, improving safety within the plant. Now, toward this end, we have chosen to spend today's program discussing condensate and its role in achieving a more effective and efficient steam system. Now, we'll start today's session with an interesting analogy, I think, of a steam system and its relevance to the human body, and then briefly review what heat is and how condensate relates to both sensible and latent energy, and the costs associated with it if it's wasted. And from here, we'll go out into the system and discuss how and where condensate is formed and the ways we capture this valuable commodity and return it to the boiler room for use in the boiler proper. Now, as you'll find during this discussion, proper condensate handling plays a very important role in establishing an effective, reliable, and efficient steam system. But be aware of the safety issues as well. Condensate, even at low pressure, needs to be understood and respected. For failure to do so can lead to surprisingly severe consequences. Now, as mentioned, if we look at the human body and its arterial and venous systems consisting of the heart, the arteries, and veins, it is similar to a steam system, with the heart representing the boiler, the motive force for the steam, the arteries being the steam distribution piping, and the veins being the condensate return piping, bringing CO2-laden blood back to the lungs where the CO2 is discharged, while the blood is reoxygenated and pumped back through the system to the organs. This is the same as the steam going out to the system. The latent energy is used in the process, and the condensate returns to the feed tank, where the CO2 or carbon dioxide and oxygen are dispersed before it is converted to steam, again in the boiler. Now, the next thing we need to keep in mind when considering condensate is what it is in terms of energy expended, and therefore the cost associated with it. Looking at this chart, you note two important terms, latent energy and sensible energy. Now, if we start with 200-degree feed water and we wish to raise the saturated temperature to 338 degrees, which is the same as 100 pounds, we have to add 138 BTUs per pound to accomplish this. Now remember, at this point, we still have liquid at 338 degrees. Now, when I apply additional BTUs at this saturated temperature and pressure, I go through a phase change from a liquid to a gas with the water and the steam at the same temperature. What I've added with these additional BTUs is latent energy, that which is used in the process. The sensible energy is actually the condensate. Now, this next chart is also very revealing. Note as I increase in pressure, the amount of latent energy decreases, while the amount of sensible energy increases. This is very important to understand when considering where the burner's energy is going and why it's important to return as much of the gold or the condensate as we possibly can. I also want you to note what happens to a pound of water when it changes state. It occupies only 0.017 cubic feet as a liquid and over 26 cubic feet as a gas. Now, that's a 1,600-time expansion, but we'll come back to that a little bit later. So talking about condensate, talking about feed water, obviously, because that condensate goes out in the system, or it comes back from the system after the latent energy has been relieved. And we want to try to bring it back as hot as possible for a couple of reasons. Notice in this steam chart, at 212 degrees feed water, a boiler horsepower is equivalent to 34.5 pounds of steam per hour. If I drop that temperature to 200 degrees, I'm only generating 34.1 pounds of steam per hour. If I were to drop that feed water temperature down to 100 degrees, we're looking at only 30.9 or 31 pounds of steam per hour, so I'm losing capacity. I'm losing horsepower because of the feed water temperature. So I've gone from 212 to 100 degrees. I've lost about 12% of my motor horsepower because of that drop in feed water. Now, of course, I can make it up with my burner, but now that's more fuel. Cost of operation in plants today is extremely important. We're trying to control our costs because competition is all over the place. It's worldwide. If we think about a corrugated container plant, a box plant, I mean, we've got competition coming from China. We've got a lot of corrugated container plants that are being consolidated, trying to control costs. And if you take a look at an average plant, whether they're a corrugated box plant or whatever, fuel is such a huge part of the overall operating expense. But also water is something that we have to think about. And what about the chemicals that go into that water, which would fall into this area of supplies? Trying to control these costs becomes very, very important, and condensate plays a significant role in that. Kind of a complicated slide up here right now, but it's easy when I take you through it. In this particular example, we've got 44,000 pounds of steam per hour, and we've got a 1,300 horsepower boiler. I don't care if it's a fire tube or a water tube. The cost of steam for 1,000 pounds today is about $15 per 1,000 pounds, which is equivalent to 1 million BTUs. Now, we're operating about 8,760 hours per year in this particular plant. We've got an operating pressure of 150 pounds. We've got total energy, that's the enthalpy of the steam, is 1,195 BTUs. Our makeup water in this particular case is 55 degrees Fahrenheit. And I said that all steam tables start from 32 degrees, liquid. So if I'm at 55 degrees, I have to add 23 degrees from 55 to of BTUs for that pound of water. Now, the condensate return temperature, let's say in this particular case, is 212 degrees. We're being very liberal here. And the BTU content being returned then is 180.3 BTUs. So, if I've got 55 degree water, of course what I have in that water is 23 BTUs that I've captured. So now let's go through the math. If no condensate is returned to the boiler plant, I'll be losing this, or if it is returned, I'll gain it, obviously. So I go through the 180.3 BTUs minus the 23 BTUs in the makeup water. So I've got a debt of 157.33 BTUs per pound that I have to add. Okay, 44,000 pounds of steam of condensate, and I've got 90% return now. This is all based on 90%. So I'm losing 10%, regaining 90%. So that's 39,600 pounds. Times the 157.33 BTUs that I have to add, or would have to add, go through the math at $15 per million BTUs, that's $93.45 per hour in cost that I can either save or I can lose. Take it times the 8,760 hours per year, and we're looking at $818 or almost $819,000 per year saved or lost. So we're certainly not talking chump change here. Now that's based on all of these conditions, $15 per 1,000 pounds or million BTUs, and a 1,300 horsepower boiler. Now the fact is that it doesn't end there. That's only the fuel. But if we take into consideration that condensate, which also has chemicals, also take into consideration the precious commodity that we have, water, and the sewer costs, and it now further inflates this $819,000 per year charge, or savings, however you want to look at it. And if we bring back condensate at even higher pressures or temperatures, the savings gets greater. And that's why we are spending time on the condensate. Now, looking at this steam system, and again, I'm going to use this example of a corrugated container plant. So we've got a corrugator here. We've got our steam coming out of our boiler, and of course, as it radiates through the piping, even though it might be insulated, there's still a certain amount of radiation that takes place. We've got condensate that has to be trapped and returned back to the boiler, or back to the boiler room in the feed system. Now, we've got a siphon tube in this roller, okay, coming off our single facer in our corrugator, and it's being trapped. Now, in many cases, this condensate line has not been properly sized for the biphase flow, and so what we'll do at this particular point is vent this flash steam off. This condensate will vent off some of that latent energy, get rid of some of that biphase, return it to a liquid so we can return it back to our feed system. So we flash that off through a pipe, and you'll see those plumes of steam, or condensate actually, coming out of those vents on the top of those roofs. That's what we're doing, so we can get the condensate back to our receiver. Now, the other thing that we could do is we could take this condensate, if the line were properly sized, and take it back to our deaerator. But chances are that the aerator has not been sized for that amount of hot condensate. High pressure returns, we would refer those to as. Maybe and normally if you're taking high pressure returns back to a deaerator, it can probably only handle between 15 and 20% of its capacity, or it's going to overpressurize and relieve its safety valve. Those vessels are normally rated at about 50 pounds. So let's say we can't do that. What else can we do? Well, I'll tell you what we can do is we can take that condensate, that hot condensate, maybe at 80 or 90 pounds, and if our line is properly sized, take it back to a high-pressure condensate receiver, which has been designed for this particular application. Now, maybe we have to use a pump trap to get it back, but the juice may indeed be worth the squeeze. So these high-pressure condensate return systems then have been properly sized, properly controlled, have all the devices on them, level devices, flow control devices, and pumps to be able to withstand those high-pressure returns. Now what we've done is not only saved those BTUs, because now we're talking maybe, could be close to 300-degree water in this tank. You know, let's say we're 80 or 90 pounds. We've also saved the chemicals, and we're saving that water. So significant savings as a result of a high-pressure condensate return tank. And then what these systems do is we will pump directly into the boiler, because these returns do not have to be deaerated. They're still hot. They've been deaerated, and sulfite's probably been added. All the chemicals are in there. They're ready to go back into the boiler. And then what happens if we use our DA to feed this tank? So when the makeup comes in at 55 degrees, it goes through our deaerator. It's preheated to about 230 degrees and then sent into my high-pressure receiver where I feed my boiler from. Now, the other thing that we could do, if we're not going to be going to a high-pressure condensate receiver, maybe because of cost, what else can we do? Well, we can take our condensate from this high-pressure return trap and put it into a flash tank. What we can do here is we can flash off that latent energy and take that energy, take that latent steam, that steam that now comes off of that hot condensate, and we could possibly pipe it back to our deaerator. Or we could take it to a unit heater. Or we could take it to a storage tank. any number of uses for that flash steam. Shell and tube heater, those BTUs can be captured in that way. And then the condensate that is left within the bottom of this tank can be used for boiler feed, or it could be used to preheat feed water. Any number of applications for that hot condensate that then is left after the flash steam is captured. Now, the thing to remember, though, about capturing flash steam is that it cannot be coming from a modulating load. It's got to be constant. And that's why I like to use the example of a corrugator, in that once that boiler is firing and that corrugator is running at so many feet per minute, it's pretty constant. And that condensate then can be flashed off. It could even be used in the hot plates, within that corrugator itself, or it could be used for the unit heaters, as I mentioned before, any number of uses, or the deaerator, depending upon the proximity of it to the deaerator. And then that condensate, of course, could be captured and used for boiler feed. But again, it's got to be continuous. Also, I want to call your attention to the fact that if it's coming from, if you're going to be capturing blowdown continuous blowdown from your boiler, because you're trying to control the conductivity in that unit, that particular condensate cannot be used in the boiler itself. You could, when you flash that off, anything coming from your total dissolved solids that are coming out, you can flash off the steam and use that, and the condensate then cannot go directly into the boiler. It could be used in a shell and tube heater to preheat feed water, but never directly into the boiler because of the contaminants within it itself. So now, talking about steam and condensate, we also have, and I've mentioned piping, velocity becomes extremely important. And the reason I say that is because the velocity in the steam distribution piping, as well as in the condensate, can cause some problems if it exceeds certain levels. One of the problems, of course, is noise. The other one would be erosion of the piping, and then, of course, water hammer, which we'll spend some time discussing. As far as the velocities are concerned, with process piping, we're normally talking in the area of between 6,000 to 8,000 feet per minute of that steam whistling down that pipe. It's between 70 and 90 miles per hour. Low pressure heating systems, a bit slower. Of course, you've got more volume there. You've got larger piping, 4,000 to 6,000 feet per minute. And then as far as condensate, the liquid, between 180 to 420 feet per minute is what we find most desirable. And biphase, a lot of these condensate return systems, as I mentioned before, can have a significant amount of steam in them. Okay, so it's a biphase mix. And in that particular case, you're looking at velocities in the area of 3,000 feet per minute. Now that then, talking about velocity and talking about these pipes that are radiating heat, the steam distribution piping, you're going to be generating a certain amount of condensate, obviously. And depending upon the amount of insulation you have on the piping, it could be even more. Less insulation, no insulation, a lot more liquid's going to accumulate as far as condensate in that piping. And notice also the 90-degree bend here that I'm showing you. So, this is probably normal operation. Now, what happens can be quite dramatic when we start talking about water hammer. And water hammer occurs in three different ways. It manifests itself in three different ways: hydraulic, thermal, and differential. Let's start with the thermal in the middle here. What thermal water hammer is when you've got biphase condensate coming into a common return. Let's say that we've got steam tracer piping from various areas dumping into a common return at different temperatures. What happens is, as soon as that biphase hits the common return condensate line inside the liquid, the steam bubbles within that condensate collapse, forming a vacuum, if you will, or a void, and all the water begins to rush to that particular point. It's called thermal water hammer. We also have hydraulic. That's nothing more than what you see in this faucet. You have that in your kitchen sink at home. Open the water up, open the spigot up, shut it off, and if you don't have a little expansion device in your piping, you're going to hear those pipes rattle a bit. That's called hydraulic water hammer. Then we have differential. Differential water hammer is when you have a delta P, a pressure difference between that particular location in the pipe where you have the accumulation of water, and then downstream from it. So you've got a motive force of that steam, that pressure, which is forcing a slug of water down that pipe. That's called differential water hammer. So what you see happening right here is, let's assume for a moment that we're starting from a cold start, a section of piping several hundred feet long. After it's been down for repair, because there's been some leaking flanges or a trap replacement. Now, we're in a hurry and under considerable pressure to get the system back up to support production. So we took a shortcut, and we didn't properly vent and drain the section that we were repairing during the warm-up. We just put the pedal to the metal, and so to speak, and just let it go. Now, note the slug of water which plugs the pipe, allowing a large column of water to speed down the pipe through the differential pressure. Now, let's say it's a 14-inch header containing, let's say, 2 gallons of water. A slug of 2 gallons of water. That's about 15 pounds, 16 pounds. It's like a bowling ball hurling down the pipe at 8,000 feet per minute or 90 miles an hour. Now it hits a valve that you forgot to open at the other end of the line. Bang! There goes the valve. That's water hammer. That's differential water hammer. It can also be exacerbated by thermal type water hammer that weakens these pipes and valves. Now that's exactly what happened in New York City on July 18th, 2007. Now remember, 9/11 was 2001. So 6 years later, we had some underground piping. And this piping was being subjected to about 230 pounds of steam. This is a central steam distribution system. And the piping wasn't properly, it was old, it was fatigued, and it got hit with water hammer. There was a tow truck on this street that flew 20 feet in the air. People thought it was another terrorist attack. There was a poor guy in that truck that got scalded with 400-degree steam. 80% of his body. There was another person who got so afraid, began to run, died of a heart attack. But everybody thought it was a terrorist attack. That's water hammer. So what do we do about it? Well, first of all, we have to capture it properly. Now, in this particular case, let's say that we're going 70 to 90 miles per hour down this length of pipe, and we're pushing some condensate, and you've got a drip pocket right here. Well, if it's not properly sized, that condensate's going to whisk right across that. So we have to have a properly sized drip leg or drip pocket to catch that condensate and then trap it out. Overall rule of thumb, when you have steam lines, 4-inch to 8-inch, you're talking 4-inch drip pocket minimum. I've had a lot of engineers tell me that they prefer going full size from 4 through 8-inch. But we're being conservative here. Certainly not less than 4-inch on an 8-inch line. So you can see the various diameters that we're recommending minimally as far as drip pocket diameter is concerned, and then the length of the drip pocket becomes very, very important too. For this reason, that we want to place our trap connection, you can see our steam trap here, we want to put it 6 to 10 inches above the bottom of that drip pocket. Why? Because we want this to collect the sediment, so we can drain it or blow that down on a regular basis. That should be part of our standard operating procedure as far as plant maintenance is concerned, proper operation of the steam system. You also want to locate these drip pockets no less. Normally, what we're saying is about every 150 to 300 feet they should be placed. And also at any low spots, the end of the main, we should have a drip pocket. The end of main or ahead of expansion joints, ahead of valves, bends, and regulators. So just common sense, really, will tell you that where that velocity begins to slow, I better have a drip pocket. So, steam traps. What do? Well, they trap steam, they remove condensate, and they remove air. Now, I will hasten to add that as far as steam traps are concerned, they are not the best air eliminators. They do help, but you should really have air vents throughout that steam system. At the places where the steam is being used, the user should have a vent. At the end of a steam line, there should be vents. At various bends, there should be vents. At low spots, there should be vents. We want to get rid of that air because it's very, very corrosive, and we'll talk about that. The trap itself will not get rid of all the air. So how do I select a trap? Well, first of all, before we start selecting traps, we have to lay out the parameters, if you will. What's the load? Pounds of steam per hour that's going to be produced. That then, of course, is going to be resulting in condensate. What's the application? Because this will dictate the type of trap used. Is it an air coil? Is it a steam line? A radiator? A steam tracer line? A jacketed kettle? What is it? Is it a modulating or constant load? Very important in terms of trap type that I'll use. And what's the back pressure? And what's the supply pressure? That'll give me my differential so I can make sure that I evacuate the condensate properly through that trap. As far as trap types is concerned, we've got thermodynamic, we have mechanical, and of course we've got thermostatic. And as far as the thermodynamic category is concerned, there's several types. The most common is the disc that you see depicted here, but there's also impulse, labyrinth, and orifice plate. Then we have mechanical traps. Those could be the float type, the float thermostatic type, open bucket, or an inverted bucket. And then the thermostatic can either be a balanced pressure, a liquid expansion, or bimetal type. So let's look at some of these. This is our thermodynamic disc trap. Very, very simple. What it has is, of course, a free-floating disc. It's got a cap, or a top, as you can see. It's got a grooved seat in here. It also has the main body. So pretty simple. Now, the way it works is a little bit more complicated. As the static pressure increases because of condensate flow into the trap, it raises the disc and allows the condensate to evacuate by raising this disc. Now, as you begin to increase the biphase flow into the trap, in other words, we're seeing more steam now, you have a dynamic action that's going on. It's called the Bernoulli effect. It's essentially what keeps airplanes aloft. As that dynamic action occurs, we begin to pull this disc down. And as we do that, we create a pressure drop. And flash steam begins to form at the cap and begins to seal this disc now down to the seat, trapping the steam. So that's how a thermodynamic trap operates. Now, for a modulating load, not bad. Now, this is all relative. It's relative to other traps, okay? So when I'm talking about good or fair or poor, it's all relative to other types of traps. So modulation, fair, back pressure, poor. Doesn't work very well with high back pressure. Dirt, very bad. So if you've got a dirty system, don't put in a thermodynamic trap because it's going to foul the seal. It wears poorly, but it can be easily repaired. But it does wear quickly. Water hammer, it's good. Air removal, good. And outside, good. Now, any trap can be used outside as long as it's operating. But this is a little bit more forgiving because it doesn't have as much fluid in it, but still has to be insulated when it's outside. Now we get into the mechanical types. The float and thermostatic and the inverted bucket. As far as the float and thermostatic trap is concerned, it works very much like a bathroom float, like a tank with a toilet float is what I'm trying to say. So we've got our condensate coming in, filling up the bowl of the trap, causing this float to rise. As it does, it raises the valve and allows the condensate to purge out. It's also got a constant vent. Now, it's a thermostatic vent. That's why they call it a float and thermostatic trap. There's a thermostatic vent here which will expand and close off when there's steam present because it's hotter. And as the condensate builds, the temperature decreases, causing this to contract and allow it to vent air. Float and thermostatic trap. Modulation, good. Modulating loads. Back pressure, good. Dirt, poor. Well, I don't have to read these all. You can read them yourselves. But water hammer, obviously, because of the float here, can be quite damaging to this particular trap. So if you get into a lot of water hammer type situations or possibilities, this would not be the best trap to be using. Air removal is excellent. Outside, poor relative to a thermodynamic. As far as the inverted bucket trap is concerned, this operates on a pressure density differential. As the condensate is, you can see in this particular case, I'm venting. This valve right here, which is tied to my bucket, is open, which means I'm now purging condensate and air out. Now, as the steam begins to increase, I'm beginning to trap more steam now than condensate. What happens here is the bucket now begins, because of the buoyancy, begins to float and closes off the valve, thereby trapping the steam. As far as the inverted bucket is concerned, modulation good. You can see all the attributes here. Dirt, poor. Air removal, fair to poor. What you're doing with these inverted buckets is there's a little orifice right here which is constantly removing the air, but it's only when we open the valve that we get rid of the air, which goes then, of course, toward the condensate line itself. And the inverted bucket also requires a prime for it to operate properly. So you always have to have a certain amount of water in the bottom of the bucket, or the bottom of the trap body itself, for the seal to form and for the bucket itself to become buoyant. As far as the thermostatic trap is, I'll get this right. The thermostatic trap is concerned, we're using the balanced pressure one here. This is an oxygen, or I should say an alcohol-filled bellows, which is sensitive to heat. As the bellows begins to expand, or is now being subjected to heat because of the steam, it expands, closes off the orifice, and you trap the steam. Very, very simple operation. Same as the air vent in that floating thermostatic trap that I showed you previously. Good for modulation, good for back pressure, pretty good. It's a trap that's used quite often in various types of applications. But they all are, and they all have their place, and they all do a very, very good job. Now, so far we've discussed the economics of condensate recovery and also discussed its formation and the means of properly securing it to not only reclaim its value, but to avoid dangerous occurrences as well. Now, we also spent a bit of time on the recovery methods of condensate, such as high-pressure condensate receivers and flash recovery. And I'd like to go back to that topic for just a few minutes before we wind things up. And let's start by referring to the drawing on the screen where you are recovering condensate from a shell and tube heater. And as you can see, I have about 15 pounds right here at the trap inlet and require approximately 12 pounds to overcome the vertical lift and the pressure in my condensate return line. So you can see I've got 6 pounds here of vertical lift, and then I've got some resistance also in the pipe. And then I've got 5 pounds in my condensate return. So I've got 11 pounds total. So I've got to have 12 pounds at least to overcome that static head and get my condensate into the condensate return line. So, but as I mentioned before, there are certain situations where either the piping is not large enough or it's just not practical to get that condensate back to my condensate return line through the piping, through its own motive force, if you will. So what do I do then? Well, that's where I have to use, a condensate transfer tank. And what you're looking at here is a pump and tank assembly, a package, normally used where condensate does not exceed 200 degrees. There are some that can be purchased that will be able to accept 212 degree water, liquid. These are also constantly venting, so if there's any flash at all, it will vent out. I want liquid. I don't want a biphase to be hitting these pumps. Now, if I get up into these elevated temperatures of beyond 200 degrees, 212 degrees, I'm concerned about the NPSH of the pump, so that's why they may have to be elevated. But they are available. But again, I'm losing that flash, which could be 10 to 20% of the condensate itself. That flash could be 10 to 20%. And that's what I was indicating before, that could be taken to a unit heater, it could be taken to a shell and tube heater, it could be taken to my deaerator to help preheat the feed water, all those. Why waste it? Now, there are certain applications where I've got, like I mentioned before, I want to take that condensate to a high-pressure condensate return system. I can use a power pump or a pressure pump for that. It could use either steam as the motive force, or it can use air. So you can see in this particular case, I've got my condensate coming in. It's like a large floating thermostatic trap. As the float begins to rise, I then will close off my vent, open up my closed check valve, so open up the discharge valve, if you will, and pump the condensate out using the motive force of steam or air. Now, speaking of air, it's extremely deleterious, if you will, to piping and boilers itself. And the corrosiveness of oxygen will increase with temperature. As you can see, I've got the corrosion on my vertical here and the amount of oxygen concentration on the horizontal axis. And then my temperatures here. So at 50 degrees, 86 degrees, and 122 degrees, you can see at 3% O2, 3% oxygen, how the corrosion increases with temperature. And also keep in mind that dissolved oxygen is 10 times more corrosive than carbon dioxide. And speaking of carbon dioxide, it comes in the border through the feed water supply as carbonates of alkalinity, or salts, and resides as part of the TDS level in the boiler. Now the problem is, when the water evaporates, becomes steam, and goes out to do its work, and then condenses, the CO2 which is formed, combined with the cooler condensate water in the piping, forms carbonic acid, which will attack the condensate return lines. And that's what you see here. Carbonic acid will also begin by attacking the weakest points in the piping, such as the threaded connections, and then continue eroding the piping, forming definite grooves and ultimate cracks or holes through which the condensate or the gold will leak. And also carbon dioxide, when put together with dissolved oxygen, is 40% more corrosive than if the two were acting alone. So now you combine the two, and you've got double jeopardy here. So, we can return the condensate now back to a condensate receiver, as you see here. But the highest temperature I can hold in this tank is 212 degrees. And it's just going to start flashing at that point. So let's say 200 degrees. That's the best that I can do. So I'm losing that sensible energy. I'm losing that latent energy as well. Now, if I went to a deaerator, it's also a tank of water. I feed my boiler with this. Now, at 50-degree water, the typical parts per billion of oxygen are between 12,000 and 20,000. Now look how that oxygen is depleted as I increase the temperature. Now what I could do with this tank is I could put a sparge tube in this tank. Let's say I'm coming back at 180 degrees, and I could heat that water to 200 or 210 degrees and drive off some of that oxygen. That's something I could do. That would be good. That would cut back on the sulfite treatment that I have to add to my boiler water, which also increases the TDS level, which increases my blowdown. But if I have a deaerator, I can take it all the way down to 7 parts per million, 0.005 cc's per liter, almost nothing, seriously reducing sulfite treatment, which then turns into sulfate, which is totally dissolved solids, which I have to blow down, plus the cost of the chemical itself. So, as you can see here by the note, modern deaerators reduce dissolved oxygen content by nearly 3,000 times. That's why we use deaerators. They feed the boiler. They capture the condensate, the hot condensate, and then we drive off those corrosive gases of oxygen and carbon dioxide. So if we take a look at the differences between going with a feed system versus a deaerator, the only negative of a deaerator against a common feed system is it's more expensive. But when you take a look at capturing the amount of gold that you capture, reducing the chemicals that you're putting into the boiler feed water, reducing the amount of water that you're using to keep this system going, these deaerators should be very, very seriously considered. If you're over 50 pounds operating, if you've got limited standby in your particular facility, it's a critical load, and you've got over 25% makeup, a deaerator becomes a very, very serious consideration. Very serious consideration. As does that high-pressure condensate return system that I spoke about earlier. And of course, the deaerators and high-pressure condensate return systems today are all controlled with PLC-based controls. So you've got all the control within a single platform, controlling your pumps, controlling the levels, variable frequency drives, logging all the data, communicating the data. This is all available to you in systems today. And it's not just Cleaver Brooks, it's our competition too. The thing we're trying to get across to you today is the value of condensate, the cost that can be reduced by returning as hot condensate as you possibly can, and then how to do it safely. Getting rid of water hammer, you don't want that in your plant. So in summary, before I close, a steam system is just like a body. Condensate is essentially the sensible energy in the water, and it increases with increasing temperature or increasing pressure. So as the pressure goes up, the amount of sensible energy that I have to add, which is condensate, is increased. Condensate forms constantly within the system. It's extremely valuable and needs to be returned as much as possible. Condensate can also be very dangerous. Traps need to be selected in size based on application. It's not a one-shoe-fits-all. And capturing condensate flash can be an excellent contributor to fuel cost reduction, and so can high-pressure condensate receivers. Finally, a deaerator not only holds condensate in boiler feed water, it drives off corrosive gases, saving chemicals while reducing blowdown losses. So how about some questions?
Thank you very much, Steve, for an excellent presentation. And I'd just like to refer back to something that you said at the beginning of today's webinar. The presentation that you've just seen is, we came about this as a result of requests that were made through our survey that we have at the end of the presentation. When you close out of WebEx, the survey is automatically sent to you. There's a place in there where you can put what you're interested in learning more about, not just rating us on how you think we did or suggestions for improvements, but there's a place for suggestions for future webinars. And we take a good look at that and really listen to it. So if you have good suggestions, we would certainly like to be able to appease you and generate material that's of your interest, that you would benefit from hearing. So with that being said, as you log off today, and we're letting questions come in at the moment, but as you log off, just remember to fill out that survey and tell us how we're doing and what we could do better and what you'd like to see from us in the future. And for those that joined later, we do conduct these webinars once a month with a different topic, with the exception of being last month. We took last month off. You can find all of our archived events at our website at www.cleaverbooks.com/webinars. You will be able to download the PowerPoint and also fully listen to the fully audio version of the presentation. All right, with that, I'm going to look through and pull up some questions and introduce to you Peter Taylor. He's on our expert panel today along with Steve Connor. Peter has been with Cleaver Brooks for about 35 years now and is a sales engineer with our packaged water system. So he's going to help fill these questions with Steve. All right, so one of our first questions we had earlier on, and let me see if I can get back to it, is, Steve, you were talking about the vents. Where do these vents usually terminate? Roof, or can you elbow it up through a sidewall?
They normally just, the vents that I've seen, we're talking steam vents now, or are we talking air vents? If we're talking air vents, they of course just vent right to the room. But as far as steam vents are, steam vents normally will. I normally see them go through a roof penetration. I have not seen sidewall, probably because of it could be a safety issue.
Okay. All right. And here's one. Steve, you were talking about a good bit of suggestions for selecting a particular trap, but nothing on really sizing one. Can you go over that just for a moment?
Sure. As far as sizing the trap is concerned, first of all, the first thing that you have to know is what is the condensate load in pounds per hour. Then you're going to apply a safety factor, which can vary anywhere between 1.5 to 1 to 10 to 1. Now, normally, for instance, for a condensing coil, they might use a 3 to 1 safety factor. And then you have to know what the differential pressure is going to be. Now, this involves knowing the inlet pressure to the trap and then the back pressure on the discharge side of the trap, which needs to be overcome. And then finally, you need to know the maximum allowable pressure that the system may possibly impose upon that trap should it fail, or should the system fail. A regulating valve doesn't regulate properly. What's it going to be exposed to? And then given that information, you can go to companies like Armstrong International, their website, Spirix, Sarco, Swagelok, people like that, and then they've got sizing software for you, or they've got nomographs that you can use to be able to select the right orifice for that trap and so on. So there's a lot of help out there. We've partnered very well with several companies that I just mentioned, Armstrong, Spirix, Sarco, and Swagelok, to help us, because we spend most of our time in the boiler room, but we've found that these systems, to help our customers, we have to get out beyond those walls and understand the system a lot better, and those companies have helped us.
Okay, next question. This one has a number of valves which are leaking in their system. They've replaced many and they still leak. Any suggestions?
Oh, that's a very good question. Every valve has an ANSI, ANSI shutoff classification with an associated leakage rating. And that classification goes, you've got Class 2, Class 4, and Class 6. Now, if you've got a Class 2 valve, it's going to have a certain leakage rate. They all leak to a certain extent. But the lower the class number, the more leakage is going to be incurred. So the leakage on a Class 2 is like 0.5%. On a Class 4, it's 0.01%, or 0.01% leakage. And a Class 6 is just infinitesimal, minimal leakage, they rank it as. So my point to you is that even though a Class 6, you should not have anything less than a Class 4 valve in your steam system. And obviously, if you go with a Class 6, it's going to cost more money, but it's going to come back in spades because of the reduction in leakage. Now, the other thing I want to make mention of, too, is that every valve has a classification. It also has a pressure and a temperature rating. Make sure that you're not just looking at the pressure. That could just be hydrostatic pressure. It's got to also have the corresponding temperature rating as well. 100-pound steam is 338 degrees, for instance.
All right, and here's another one. Can you elaborate on corrosion rates if dealing with hard water? Will this one be you or Peter?
Corrosion rates with, I really can't, in all honesty, Susan. I don't have anything on the corrosion rates, actually. I mean, I certainly could find it. And that's one thing that we do as well, is that these questions that you pose, we will answer those on our website after this discussion is over. And I'll make sure that we address that, because I've got the information somewhere.
Okay. And you showed a diagram previously, which has piping to and from a heat exchanger. This person has problems with waterlogging. Any suggestions?
Let's see if we can get back to that. Yep, there we go. Yeah, right here, you can see this heat exchanger that's kind of filling up with water, with condensate, which means that my trap is backing up, okay? It's got, the back pressure is too great, and I'm starting to back up into my heat exchanger. And that's referred to as stall, S-T-A-L-L. This means you're losing the differential across the trap body, probably because of a modulating valve, and that's exactly what you see here. I've got a modulating valve, so I'm losing my differential, which is varying the inlet pressure to my trap. So you can either resize the trap to meet the varying load conditions or install a power pump with the existing trap, and the power pump would then handle the varying load conditions, okay, where we don't have the proper differential across the trap, and where we do have the proper differential, then the trap itself would then be evacuating the condensate. So it would be in tandem. We would have a power pump along with a steam trap to eliminate the problem of stall.
All right, we've got time for a couple more if somebody's waiting to ask one. This may be a good one. On a low-pressure system, is it really advantageous to replace trap parts every year, even with rebates involved, or do the savings really add up, or can it be every 2 or 3 years? What's your rule of thumb there or suggestion?
Boy, I'll tell you, Susan, can you repeat that, please? I didn't hear it. There was some static here.
Okay. On a low-pressure system, is it really advantageous to replace trap parts every year? Do the savings really add up, or can it be every 2 or 3 years?
I'll tell you, I would be reluctant to say that they had to be rebuilt every year. But certainly a good, diligent trap testing program should be put in place. And that starts with an inventory of where your traps are. And then those should be tested. Normally what we're finding today is you can shoot them with an infrared gun, and you can see, you know, the difference in temperature on the upstream versus downstream side of the trap. That'll tell you something whether or not it's leaking through and needs to be rebuilt or replaced. But ultrasonically is probably the best way to test those traps. And based on the operation of the trap itself would then dictate whether or not the trap should either be rebuilt, like in the case of a thermodynamic trap, or whether it should be replaced. But to say just as a gross statement, overall statement, to replace these or rebuild them every year, I think that's a bit extreme.
All right, we are now up on, well, a little over the top of the hour. So as Steve mentioned before, if you have questions or you're reviewing a PowerPoint from the website and you have additional questions or need further clarification or need to speak with someone, at the end of the presentation is a contact name, and for this one it's Peter. You can find his phone number and his email address. And if need be, we also have, we'll have other engineers get back with you. So feel free to take a look at the PowerPoint and spend a little bit of time reviewing it. And if you have additional questions, we'll be sure to get back to you. And we'll also have those, as Steve suggested, we'll have those on the website in a Word document file that you'll be able to download as well. That being said, I appreciate you all joining in, and we do have a topic for next month's webinar. We've had a number of requests for energy recovery, so next month we are going to do one on large-scale energy recovery, and if I'm not mistaken, that will occur on February the 27th, Steve, am I correct?
Yes, you are.
All right, good. So we will see all of you, hopefully, back on our next webinar, large-scale energy recovery, occurring on February 27th. And hope you all have a fantastic day, and refer to our website for additional information. Appreciate it. Thank you.